Good afternoon. Today we continue the data reduction part of the machine learning. Last lecture we studied the feature selection methods and also the principal component analysis. And we mentioned that the principal component analysis is a method that is unsupervised. So you don't need to know the output in order to make the reduction of the data and remove like any linearities or redundancy in the data. And today we see that or study the linear discriminant analysis. Linear discriminant analysis, the main thing here that it is applied mainly in the classification and when you have different classes of data. So the linear discriminant analysis is a supervised method, as we mentioned, and it is simple to apply, but it is also powerful technology for linear classification. It has many applications, for example, in dimension reduction from D to 1, of course in case of two classes, or feature reductions, extraction from large data, for example, from images, which can be used later as image recognition. And also it is widely used in marketing, for example, to classify different customers or services on the basis of a survey. So if you have a survey, then you like to classify the different customers or all products, for example, based on the survey. How it works? Okay, here I will start with only two classes. Then we generalize to any number of a class. Assume that you have samples that they are classified into two classes, C1 and C2. And we want to find the direction, okay, of a vector W such that when we project the data into that space, so the data which are belonging to the same class should be as close as possible to each other, but the data from different classes should be as apart as possible from each other. I repeat. So now we have data like this one. Okay, see that we have such data that here we assume that we have only two classes of the data, so we have C1 or C2, okay? And we have some like features or attributes. For example, here we have x1, 1, then x2, 1, until xd, 1. This is the first sample, and then it belongs to one of the classes. For example, C1. And then we have the second row of samples. It is x1, 2, x2, 2, until xd, 2, and it belongs, for example, to class 2, and so on. Okay. Now we have only two classes. What is our aim? Our aim is like that. We like to have, for example, this x vector for any sample number t. So it contains inside like x1, x2 until xd. So the dimension here is a vector, so it is d by 1. Okay. So our idea is to find the optimum vector w. It is a weighting vector. When we multiply this weighting vector in x, so we project this from d dimension to 1 dimension, because this w transpose w also belongs to r as like d by 1. So when we take the transpose, it becomes 1 by d. So when you make the multiplication, you will have a scalar, in that case z. Okay? So this will be like zt. This will be zt, that for sample t. Okay. What is our aim? Our aim is to make this projection for every class. In the beginning, we start with, for example, class 1 and class 2. And our objective is to make the projection that if the data belongs to the same class, they should be as close as possible to each other. And if they are belonging to different classes, they should be as apart as possible from each other. So this is our aim that we want to do. And actually, this is the concept of linear discriminant analysis. And why we call it linear? Because we multiply it with W, so it is linear process. So we achieve this by a linear process, or linear projection. Okay, so this is the concept. Let us see how to do it. If we start with the samples like X capital, that we have data X and RT here is the class number. So if the data or the input belongs to class C1, then we have RT equal to 1, otherwise RT equal to 0, because here, as I said, we assume that we have only 2 classes. Okay. Then we can compute the maximum likelihood estimate of the class average. So we come to each class, for example, for C1, and we compute the average. How to compute the average? For example, we have this number, assume this is also C1, assume this is also C1, then simply this one plus this one plus this one, all vector. You take the summation, and then you divide on the number of a class 1. So here, for example, you have 3, and class 1, then we divide by 3. So this is called this is the mean of class 1. And this is the maximum likelihood estimation for the mean of class 2. So in this way, we computed the mean of each class. Okay. Now, the projection of the mean of the class by the same weight vector, this is the weight vector that we are looking for. If we make the projection, then we will have a scalar. And this scalar is called M1, and this is M2, which means that it is the mean of the data after projection. The mean of the data after projection. Okay, we can also compute the variance. We can also compute the variance of each class. The maximum likelihood estimation of the variance is simply like that. So we, after projection, of course, so you take, for example, for this one, you take the data, multiply it by weight, and then minus mean of class 1, and you take the square. So it is the variance of the data around mean M1 for class 1, and this is the variance of the data around the mean M2 for class 2. Here we take the maximum likelihood estimation as unbiased estimate, so we subtract by 1. But when you have a lot of data, it doesn't matter if you subtract by 1 or not. So now the summation of RT is the number of samples in the class 1, and the number 1 minus RT is the number of samples in the class 2. The total number of samples is N1 plus N2. Okay, now what is our aim here, or what is our objective? Our objective mainly is to keep S1 square and S2 square as close as possible to, or as small as possible, because this gives the scattering, or this gives the variance of the data around its mean. And now it is like supervised learning, because we know each data belongs to which class. So for example, we like to have, for example, this data, we like to have them, for example, for the cross class to be very close to each other, and the other class, for example, circles, to be also very close to each other. So the variance here is given by S1 square, the variance here is given by S2 square. Then our aim is to minimize S1 square plus S2 square. But because this has a mean, for example, M1, and this has a mean M2, in order to minimize the error in the classification, we try to maximize the difference between them. So we want to minimize this one, but also we want to maximize M1 minus M2. Maybe you take square or take the absolute value, doesn't matter. Okay? So we like to achieve these both objectives. Of course, there are different techniques. You might use multi-objective optimization, for example, in order to achieve, to minimize one objective and maximize the other objective. But we follow the textbook. So the textbook uses this well-known Fisher linear discriminant equation, which is given by this way. So they define the objective function, KW, equal to M1 minus M2 square, as it is shown here, divided by S1 square plus S2 square. And our objective now is to minimize this one. Sorry, to maximize this J. Maximize this one, what it means? It means that you maximize the upper part and also you minimize the lower part. Then you achieve the maximization of the Fisher discriminant function. So this is the concept here that we would like to have. What is W which achieve or which makes this maximum? Maximizing this Fisher discriminant function. Okay. Okay. Now we are looking for W. Actually, we are looking because we maximize with respect to the weighting vector W. So what we do, we just substitute W inside here. So we know that M1, as it was given, M1 is W transpose times M1 vector M1, and M2 is W transpose times M2. So we just substitute them here, and this can be expanded easily if you revise lecture 1 in the last part where we give some notations, linear notations, so you can find easily that this can be expanded like this one. So it becomes like W transpose M1 minus M2 times M1 minus M2 transpose times W, and this gives you this M1 minus M2 square. Remember here that the rank of SB is equal to 1 because it is just one vector times one row. One column times one row, so the rank is equal to 1 for SP. But this is M1 minus M2 square, and now we compute also S1 square plus S2 square in the same manner, because here you can, there is square here, so because M1 equal to W transpose times M1 vector, so you can take W transpose as W transpose and W as a common factor, and this will be in this way. And this will be S1 square. So S1 square is equal to what? W transpose times S1. S1 is the covariance of the data in class 1. The covariance of the data in class 1. S2 is the covariance of the data in class 2. So this is the way that we compute the variance of each class. Now we substitute this because we need to take S1 square plus S2 square. So S1 square, as it is given here, it is W transpose times S1 as the covariance matrix times W plus W transpose S2 times W. Then we can take W transpose and W as a common factor, common vectors. So we have here S1 plus S2 times W, and this we call it like SW. Is the summation of the covariances of both the classes. So it will be in this way. Okay. Now we like to maximize the Fisher linear discriminants. How to maximize it? Simply by differentiating. So we differentiate this scalar with respect to vector W. Okay, and when you make the differentiation, you can easily prove it. So you will get this result. Of course, we take the differentiation and we put the result equal to 0 in order to find the stationary point, which will be the maximum point in this case, because the minimum should be 0 in that case. Okay, so here, if you look to this W, if you look to this one, this factor, of course, now this equal to 0, then you have either this equal to 0 or what is inside equal to 0. So we take this, what is inside equal to 0, to have a solution, and look to this factor, W transpose times M1 minus M2 divided by W transpose times SWW. You can see that the dimension of this transpose is 1 by D. The dimension here is D by 1, and also the dimension here is 1 by 1. So all this factor actually is a scalar. All this factor is a scalar. We are looking for the weight, actually the optimum weight here. We are not interested mainly in the value. We are not interested in the magnitude of this weight, but we are more interested in the direction. So the direction is the one which will specify in what direction we should project our data in order to maximize the difference between the classes and also minimize the variance of the data in each class. Because of that, we are not interested in this as a scalar. So as a scalar, it doesn't matter. It can take any value. For this reason that we ignore it. So we just put it as a C, as a scalar C or constant C. And then we solve for W, and then the optimum weight, in this case that we obtain, is given by C times the inverse of the total of the covariance matrices times M1 minus M2. This gives you the optimum weight vector that achieve our requirement to maximize this function. Maximize this function, which means maximizing this and minimizing the variance of each element. I think there can be like open research here. If you are interested in math, for example, you can try with different. There are already many published research in this area, but you can think about using multi-objective optimization, that in order that you minimize this one and at the same time maximizing this one. Actually, this will give you one interesting parameter, because if you have two objectives like f1 of x and f2 of x, and you are interested to maximize this one and minimize this one, for example, then you can build one of the techniques that you can build the multi-objective optimization, that you should maximize f1 of x minus lambda f2 of x, but here it should be multiplied also by 1 minus lambda. This lambda is not the Lagrange multiplier. This lambda here is the compromise between two objectives. So you can make the compromise. So in that case, it gives you like one more parameter that you can say that if you are interested more in minimizing the variance of each class, or you are more interested to keep the means of each class as above as possible. Okay. Actually, if we assume that the data in each class is normally distributed, so that the distribution of the x given a class Ci is is just normal distributed with mean mu I vector, and it has variance z, covariance z. In that case, if we assume that we have identical covariance matrix for each class, if you compute the optimum linear discriminant that we have already given in part 4, you will get this result. So it will be the covariance inverse times mu1 minus mu2, which is nothing but it is the same result that we obtained here. It is the same result. So this means that Fisher linear discriminant is the optimum in case that the data is normally distributed, and also you have the same covariance in each class. But of course, it's not necessarily like that. So the good thing that with Fisher that it works fine also with different kinds of distributions of the data. Okay. What if we have more than two classes? If we have for example, 3 classes or 4 classes, a general way. In case that you have general number, or in order to solve this in general cases, so now we are interested to find not single vector, but we are interested to find a matrix in this case. So this matrix, for example, if we have k classes, then this matrix W should be D by K. D is the same dimension of the data itself, and K is the size of the number of classes. Okay, now we are interested in this Z. Z is not scalar anymore. Z now is a vector, and this vector is W transpose times X, and our concept here is exactly the same as we did in the case of 2 classes. We like to achieve the mean of each class to be as far away as possible from the means of other classes, and in the same time we are interested to keep the variance of each class as close as possible to other classes. But before I continue here, I forgot to mention one thing about this linear discriminant analysis, that where is the reduction of data? Where is the reduction? Actually, the reduction that you have vector, in case that you have 2 classes, you have vector of D element. D can be 3, 4, 10, whatever number of features that you have, and when you multiply them by W transpose, actually you project all this D dimension into only one dimension. So we make the projection from d-dimension data into only one dimension. So this is the reduction part. So reduction, that when we have this projection from d dimensions to only one dimension. Okay. Yes, the same here, but here the projection is not into like one dimension. Here we like to project the data from d dimension into k dimensions. Is the number of classes that we have, because we like to see in which class each data is belonging to. However, the concept is exactly the same as we did in the two classes problem. So we start with the computation of the variance of each class. So we compute the variance of each class, and then we compute the within the class covariance, which is the summation of all the classes, the variances of each class. We take it just the summation. And also we compute the mean of all the classes. So which means that we compute the mean for each class, and then we take the summation over all the classes divided by the number of classes. So we have the overall mean of the whole data that we have. Okay. Then we can compute the between the classes scattering matrix. It is the number of data in each class multiplied by mi minus m times mi minus m. So you can see that here you take the summation over k classes. Okay, so we have here, and ni is the number of elements in each class. Again, we come to the same equation, like in the two classes case. We like to minimize. We like to maximize the Fisher function, but now we have this W. Now we have matrix instead of vector. So we have this matrix W transpose times SP times W, and W transpose times SW times W. So now we like to maximize this one instead of maximizing only a scalar element. Now it is not scalar anymore. It is a vector. Okay. How to do it? Actually, this in general, if you have in linear algebra such kind of equation that you have vector transpose or matrix transpose times SW times W, okay, and we want to have this as small as possible, and of course, as I said, sorry, we like to have this one as big as possible, okay. And after projection, actually, we want the samples to be as far away as possible, as I mentioned. For a scatter covariance matrix, a measure of the spread here is not variance. Okay. Usually, we have the variance to measure the scattering in case of single element, but in case of matrix, we use determinant. We use the determinant is the way to measure the spread of the elements there. So in order to maximize, we need to maximize the determinant in order to maximize the scattering. For example, if we want to maximize the scattering, or minimize the determinant if in order to minimize the scattering. Okay, what is the determinant? The determinant is of a matrix that, as we know, that it is the elements. The determinant of a matrix, of any matrix A, for example, is equal to, when you solve that it is the same as like lambda, the determinant, okay, in order for the determinant of lambda I minus A that equal to 0, then you find here the eigenvalues of this, and then you can find also the eigenvectors. And there's we know how to compute the determinant in general. So of course, if it is like 2 by 2 is easy to find by hand, or even 3 by 3. But more than you need to use some mathematical packages. And also we know that the determinant of any matrix A if A is square and n by n dimension and non-singular, this equal to lambda 1, lambda 2, until lambda n, the multiplication of the eigen values of this matrix. As we explained last lecture when we talk about the trace of matrix, we said the trace of matrix is the same as the summation of the eigen values, but the determinant of matrix is the multiplication of the eigen values. Okay, now we are interested to maximize this one without going into mathematical derivations. So the eigenvectors, this W will be the eigenvectors associated with the largest eigenvalue of this value of SW inverse times SP. So in general, the W, the solution to this linear equation, or in order to maximize this one, the solution will be the eigenvectors that will formulate the matrix W. And which eigenvectors we select? First, we compute SW inverse times SP. Okay. Once we compute this, we calculate the eigenvalue of this function. So we compute the eigenvalues, and then, as I showed you last lecture, when I use for example, the command eigen in Octave, then you will have the eigenvalues as diagonal, and then you have eigenvectors. Okay, in another matrix. What we do here, we select the maximum eigenvalues. For example, of course, we are looking for the k, for the dimension k. So we look for the largest eigenvalues. And then, for example, if this one was the largest, is the first, then we take the first column in the eigenvector matrix. If the second was small, so we ignore it. If the third is high, then we take the third eigenvalue, and those third eigenvector, and those eigenvectors will formulate the optimum matrix W. So this is the way that how to compute it. However, of course, as we mentioned before, in many packages they are already built in. So LDA, you can find them like ready function that you can compute with your data. But this is the concept how to compute the optimum W in this case. Okay, let us have a numerical example to see how it works. So now this is only two classes. Find the optimum projection weight for the following data table. So we have here x1, x2 equal 1, 1, a class C1, and 1.52 class C1, and this one also class C1, and the other class C2. Okay, so what we did here, we just compute the mean in each class. Okay, and then we compute also the covariance of each class, and just we apply the previous formula that we saw, and then we found that the optimum weight will be minus 1.73.09. And when I made projection for this W over this data, so you can see this is the original data. Class 1 is the blue, and the red one is class 2. Okay, and after projection, you can see that we classify the data, and this is the optimum that what we can do with this data. So this is the optimum, this is the minimum variance we can achieve, and this is the maximum separation we can achieve based on the available data. This is the maximum linear separation. Of course, you might use some other techniques, or you might use also you can take a higher dimension. For example, if you take the dimension of x squared, as we explained before, or x cubed, or you take the logarithm. So you can, of course, you have many number of freedom that you can do. But with the simple linear projection, this is the best what we can. This is the best what we can obtain for this data. Okay. In case of, I will mainly skip this one, but I recommend that you read it. In case that you have non-linear type of data, how to solve it with linearly embedded method. So simply that we can divide the regions of that non-linear shape into some small linear areas, and then we can work with the same way that as we did here for the linear case, but it will be for only locally dimensions from the total data. And in that case, we need only the tricky point here is how to find the neighbor points for each feature in order to see that they are belongs to the same features. And as I said that I skipped this one, but here we come to the exercises that we have data, part 5, it is on model already, and we have it has dimension of 15, so we have the dimension of the features is 15, and they belongs to 5 different classes. Okay, so first use principal component analysis to reduce the data of the file. Okay, and then build discriminant function as described in part 4, not linear discriminant analysis here, but discriminant function that we described in part 4. And then validate your code of reduction with another data. So actually, I bought 2 different kind of data for learn and data for testing. So try the data for testing. It contains 400 data samples, and try to check is the projection of the principal component analysis was valid or not. And exercise 2, repeat the same with linear discriminant analysis. Actually, for the BCA, we don't need this information of the classes because we are working as unsupervised learning or data itself. But for the LDA, we need this classes information in order to build the proper function. And also repeat the previous exercise with using sequential forward-backward selection to reduce the data, and then compare all the results together, which one was more powerful method. So you don't need to bring it to me, but if you work with it, so you can also discuss with the instructor about this course, about the results, and of course you can take them as topic for your report. Course report, you can select this as the topic for your report if you like. Okay, that is all for this part. And actually, my plan was to also start the part 6 today, but I have a little bit like beginning of a flu, so I might not be able to continue today. But there will be a quiz already, so it is already now on model. Is it valid until Saturday? So until Saturday, so you can when you open, it is one trial. How long?
1 hour.
1 hour. Okay. So this will be a quiz, so you can try with it. Any questions about today? Okay. Thanks a lot. Thank you.